in the tree, the amount of information in the tree is how we decide to split. So the tree should be encoding most of the information in your data, okay? And then the way that we decide to split is, there are many ways, but they all related to the fact that what we are trying to do is to maximize the amount of information in the tree. So we have information gain, Gini gain, and the chi-square score. There is a difference. These two, we don't account for the problem of having too few samples, right? These metrics are subject to problems if you don't have enough examples. And this one accounts for how many examples you have. Okay? Many examples is why, because if you don't have enough examples, you're not too certain about what is the information gain that you have. If you had more examples, you would be more certain about that. Another classifier we saw is a naive-based classifier, where we are conditioning that we are looking for some class. Let's say someone buys a computer, given all these other attributes, and then we make a naive-based assumption where we say that given this class, all the given if you buy a computer or no, then all the features, all the rest of the features are independent given this class. Okay, it's a big assumption, but that makes the math really simple. So we only need to compute the probability of A given buys computer, probability of income, given by computer. So just counting these frequencies for each of these types. No, you count all the frequencies of income. For yes, you count all the frequencies of income. So you're just counting frequencies. The likelihood function is something like this, and here until here we have the assumption is only that the data points are independent. And here the assumption becomes that the naive-based assumption, where we are saying that the features, the J's, which are the features here, are all independent given this class. So, okay. All right. Zero counts are a problem for naive-based classifiers. There is no such a thing as zero probability. Never predict zero. Okay? It's a big problem. How does that affect the conditional probability? Because if you don't see a value, then you assign probability 0 of that value happening. And then it's a problem because if you ever see in the future that item appearing, probability 0, if you're computing some kind of loss, some loss functions could be infinite value, because you saw something that was not supposed to happen, right? Never say never. I think that's the main thing about predicting probability. And then if we take the beta view, then the zero counts are not really a problem, because we have a prior. We can assign a prior to the probability of any feature showing up, right? Like we can, for instance, use the beta prior, and if you use the beta prior, so probability that you buy a computer, you don't buy a computer, or how many you had n people that didn't buy a computer. Given n people that didn't buy a computer, what's the probability that their income is high? There are people that have high income, okay? Then it will be just if you go. So this is the beta, the part of the beta distribution, and this is going to be your binomial, because this thing is binomially distributed. Then the beta prior solves the problem, basically. What are you saying when you're saying that there is a prior? You're saying that there is, even if you never see any data, there is some probability that it could happen, okay? In the end, it's just adding one and dividing by the sum of whatever you added. So it really is simple. But I just want to explain in that capacity, like why you should create data in that sense. So when you have a lot of, now we go to model selection now and assessment. In data-rich scenarios, you can just split once into train, validation, and test. You have a lot of data, so you don't care. Right? You can do the model selection here, training, validation. We have done that a lot. And then the assessment is this test should never be used to select models. Okay? Once you have your final model, what you want to test, or the two final models, or three, then you go to the test, and you do that only once to assess whether your model is good. In data poor scenarios where you don't have as much data to divide things around, notice that that data rich is a as we'll see is relative. It's relative to how complex your model is. Maybe a lot of data for a billion, 15. Google has a 15 billion parameter neural network. 15 billion parameters. For a 15 billion parameter, a billion images is not a lot of data. Okay, so just depending on the complexity of the model. So in data poor scenarios, we try to approximate the validation step. Analytically, we use AIC, DIC, or MDL. With sample we do cross-validation like leave one out, or k-fold, or bootstrap. Leave one out is k-fold, one k-fold m. So another thing, when you have two algorithms that you want to test, whether one is A is better than B, with k-fold you can use a parity test, because you can go the training, and then the validation you will get errors for each of the algorithms and each of the folds. And then these errors will provide an estimate of the errors, that you have in the test. The mean estimates the expected error, and you should ask yourself, like, is the mean error significant between A and B? And then you have to use hypothesis testing, right? To test it. And we saw the parity test for that. Now, decomposing the test here, we have this notion of a bias of the model and the variance. With a lot of data, simple models can perform surprisingly well due to the lower variance that they have. So here's an expression for the bias for a simple error and a simple model. Just to have show kind of intuitively what the bias and the variance validation, you can try to correct this bias. Remember that we are looking for the threshold of the P for the logistic regression, the probability that you say class A or class B. So what we are trying to do there to say, well, I'm making mistakes, but I'm making kind of, I know where the mistake is. And then I can try to improve this. Although there are automatic ways to do this, but you can do manually validation. So that happens a lot. That's easier to be fixed in validation. This is harder to be fixed, right? Variance is harder to be fixed if you there is really not an easier way. Okay, so we also saw learning curves where we have the training. We increase the amount of training data, and then we look at some kind of error or metric of goodness, and then we see that we look at that over the training data itself and over the validation data, right? This is extremely important to understand what this curve is telling you. So what is that we are seeing here? What is it? So what is this telling you about your model?
Number of points are larger than forward. Samples are being larger to convert.
Right. If you add more data, then this thing will eventually converge. You can already see that there is not much gain for having more data. You see this? If you are paying $10,000 for 1,000 points, you will be wasting money every time you get more data here for this model. Now, what can you do, right? You notice that here, after this, you're not getting any gain. What should you do? Right, increase the complexity of your model, because then this thing will go up, hopefully, if your model behaves. It will go up. This will be like this, but it will go, hopefully will go up a bit, right? So it will get to the right point. And that's what we actually do in practice. We'll look at this curve and say, oh, the model is not complex enough, we should make a more complex model. Because we have enough data, okay? What would happen if the model was too complex for the data? Overfit. So how would you see overfit here?
The validation at school will go down.
It would be something like this, right? Where if we stopped here, we can see that there's a big gap between our test, our training, which we think we are doing awesome, and when we look at validation, is not nearly as good, right? It's telling you that you are super confident because you are overfitting your data. This is the first thing you do in real life when you are using a classifier.
Professor,
Yeah.
why are you saying that this graph is open, right? At the point after 2000, my data is converted, right?
Yeah.
So why do we need to worry to maybe more complexity?
Well, because see, if we have this if you think about logistic regression, right? If I added in the interaction term between the features, that interaction term could now transforming your data into something that's adding a nonlinear term. So now your hyperplane has more possibilities. If you give a zero weight to that nonlinear interaction, then you have the same, nothing changes for you. You still have the same model, okay? But if you add something that is not zero to that term, then you can now have a hyperplane that is not linear in that space anymore. It's non-linear. You see? So you're adding capability to your model if needed to have a different hyperplane that's a bit more complex, right? And in that case, when you add this capability, if you have enough data to distinguish whether that capability is important or not, then you should get better performance. These curves will go up, and they will spread a bit, and they will go up a bit. Okay?
So when do we understand that we have to make our parameters more complex?
Yeah. When I say up, is because the F1 score up is better. If this is mean square error, it goes down, right? Because the error, mean square error is bad.
It's also our choice. When we're doing the practical life, it's also our choice that we want more F1, better F1 score or not. If we want to add more complexity or not.
Right, yeah. Adding complexity is something that is always possible because you can add complexity through the features. You don't have to really change much in your code. You just make interactions in your features, and that is adding complexity because you have extra parameters to.
So we are making our model complex. Surely the training performance will increase, right? But does that mean the validation performance will always increase all the time?
Right. So that's a good point. So the question is, if we make a more complex model, well, very likely, for sure, actually, we'll have a increase in our training data performance, because as I said, you have this extra term that you can use or you may not use. So if you use, then you can better fit your data, then the model will use, if the estimation is doing correctly, it will use to better fit the data, right? Then it will go up here, and now we have, now the question is whether this will move. Now, if the extra complexity is doing nothing, right, it will not move. But if the extra complexity is helping you better, let's say that you had at some point here, right, so you had a class, the circle classes and the X classes, and now by adding some non-linear interaction, well, we have some linear interaction already, so your hyperplane is not like this, it's something like this. But if you add another interaction, now you may be able to make your hyperplane outside. You should do something like this. But if you add other nonlinear interactions, you may be able to get your hyperplane to do this. So it will more likely better fit the training data for sure, but maybe even the validation data, it would be better for the validation data. But the thing about how much training data you need is that if you have enough training data, then you can tell whether this is relevant or not, right? Because if it's something like this, then you say, no, don't do this. But if it's something like this, then you are sure that this is a good thing to do. So once you have enough training data, you can distinguish whether you should use that added complexity or not, and therefore this will tell you whether this added complexity is helping. Generally in practice, most added complexities help as long as your estimation procedure for that more complex model is as good as the one that you had. The estimation procedure for the optimal values, right, the parameter values for the more complex model are still doing a good job.
But one question.
Yeah.
When you are working like in a high dimensional space, like you have an SVM and you're using this magic kernel that moves your data to this infinite dimensional space,
Yeah.
how do you know about the complexity? I mean, if you have a result like this, how do you know that you can increase complexity?
So you're talking about the kernel. So here when you have this infinite space kernel, you should change the kernel. That's what you can do. There's not much else that you can do with an SVM. Okay? You change the kernel, you look for another kernel. Okay. I think this is extremely important that you understand this and study and think about all the possibilities all that you can learn from this curve. There's a lot of information in this. even if your model is doing something weird, you're not learning the parameters correctly. What would you expect from the curve if your estimation is doing something crazy that doesn't make sense? A bug. If a bug on your code. Like your model is wrong, like your estimation is wrong, right?
Both the test and training would be bad.
Right. So when you give, if it's a very complex model and at this point, it's not monotonically decreasing, right? Or you don't get good performance in the training. I've seen students come with things that where the training there is like lower than the validation. Okay, that should never happen, right? Never, ever, possibly ever happen. So you can find a lot of bugs and problems in your method by looking at this. Okay?
One last question. This is almost the ideal graph for system validation.
Oh, yeah.
Initially,
This is, surprisingly, this is real data. But yeah.
I think that the trainer users want and the validation users more at the beginning, but at the end it goes up. So
Right.
this is almost the ideal graph, the ideal design.
Yeah. Yes, this is good, yes. You will see this in practice in most cases. Absolute majority of the cases, unless you're doing something that you cannot learn the parameters well. Like deep learning, this curve here goes like kind of everywhere and it wiggles around. Right? People that have used those models know that. Because you're not finding optimal points. You're far from the optimal still, and there are many issues with that. But if there's no issues with the learning of the parameters, the optimal points, then things should be smooth like this. Another thing is, imagine about penalties, right? Regularization. To regularize this, what happens? It's very strong regularization. You have done this in the
Then
homework.
it will not overfit.
Right, the
The
gap
gap
is
will
well,
be-
now the model is simpler, so,
Yes.
right, so with less data, I better fit, and then the gap reduces. So if you add a lot of parameters and you see it, you cannot buy more data, you see that you are here. Okay? But, and your model is that was the model that we all decided in the company that is working really well, that should work really well. Someone told us that's the model we should use. We just paid $1 million for this model. What should we do, right? We can't buy more data, the gap is like this, and we have this model, so what do? We regularize the model to make, right, to make it simpler. The same with the same number of parameters. Okay, so there are some assumptions that the training data is representative of underlying population of the validation. It might, or the test, it might not be. The assumption 2 is the parameters are free to assume the optimal value. There well, is an assumption about this. Yeah, so if you add prior, then this thing changes, it will likely narrow the gap. Now we talked about dimensionality reduction, principal component analysis, which gives you orthogonal vectors from projection, independent component analysis, which is a weaker form of independence, which is a stronger form of independence. It just makes sure that things are uncorrelated, but they don't have to be orthogonal. I tend to like better ICA, some people like better TCA. But I think that, why is the right projection orthogonal? class can be basically anything, and you have just a probability that we see that given class, and this is how we're going to mix. So that gives you a way to describe your data. Note that the clustering assignments are latent, so you don't see which cluster the variable belongs to. So you have to learn that. And then you probably do is to learn this by expectation maximization. This is an example with the Gaussian mixture model.
Can you explain what does probability of cluster mean?
Oh yeah, so it is how many of the users are of the given cluster. So let's say that we are in this classroom, and then you ask, well, let's cluster students and professors, right? What's the probability that a real random person here is a student? What's the probability that a random person in this room is a professor? So you're trying to learn that to better cluster your data. Okay? Hard clustering is something that so in soft clustering, what happens is that if you compute the posterior probability of a cluster given everything, I'll give a probability that you are a professor. And it will not be zero. It will be something different than zero. So you could be a professor. And that's why soft clustering, because we are not saying you are not a professor. You cannot be, you must be. We are all giving a probability that you are. Now, in hard clustering, we are saying, no. You have one class and one class only, and you have to decide which one. So you have to give a notion of distance between the points. There are a number of heuristics to do this.